Okay, so Tuesday, I guess we talked about some channel models, statistical channel models, and some um, empirical models, that type of thing. And we see these models and we say, boy, that's there's some nasty stuff in there, right? So when the signals reflect off of different scatterers in the environment, they can kind of have a bad luck and cancellation, and you can have a very deep fade, right? Now, we have a lot of mobile systems these days, and every time you're moving, that summation cancellation type of situation can change, right? So, and at high data rates, that can be a real problem. So, today we're going to talk about diversity and how we can use a specific instance of that we'll introduce on using multiple antennas in our system. So let me go ahead and I guess I should share my screen. And actually, before we get started on that, I have been putting together a assignment on spread spectrum, and so I still having problems getting connected to remotely. So I haven't graded the last assignment yet, but hopefully ITS will get that fixed soon for me, figure out what I'm doing wrong, whatever. So on this next assignment, we're going to basically start with the example from the book itself, right? So, and if you look at the textbook, there's all sorts of MATLAB examples at the end of each chapter, and but I haven't been able to find a resource where we can just download those. I don't know. They're probably on a website somewhere at the publisher, but they're not in his instructor resources. So I manually typed it all in and then made some enhancements. So I'll write this up and put it on Moodle soon, and then give you about a week to work on it. But it's basically going to take a QPSK type signal and generate a bunch of symbols. 20,000 here, I think, is how the example starts off. And then it uses a spreading factor of 11. Now, when we spread these things, we talked about using these kind of orthogonal codes. We didn't really go very deep on what makes a good code. There's certain autocorrelation and cross correlation properties that make a good code. In CDMA, we have a whole family called gold codes in the kind of 3G type standards, which are a little bit archaic at this point, but CDMA is still used in one form or another in a lot of systems. In this case, they use a 11 chip Barker code, and Barker codes are a family of codes that have these good autocorrelation and cross correlation parameters. And you see here that this P code here is basically a sequence of ones and minus ones. There's a little transpose operator out there, so we can kind of write it as a column or a row vector, and then transform it into a column vector. We generate some symbols up here. Since it's QPSK, this is how the book is doing it. They're generating real and imaginary things here, and subtracting one to get this scaled right, so that basically you're going to get a bunch of combinations of ones, minus ones, plus one, plus J's, minus J's, but they're in a QPSK type situation, so they'll look something like actually like this over here. So you'd have 1 plus 1 I, 1 minus 1 I, dot dot dot. Let's see, we can see a few more of them right here. So then they use this cron function to actually do the spreading. So just a little bit of a nice trick. And here's, you can look up this Kronecker tensor product. And so you've heard this name before in the Kronecker delta type function, but here we're, it's not what we would conventionally think of as a matrix multiplier, multiplication, or a vector times a matrix or something like that, right? It's actually generating a much larger matrix formed by taking all possible products between the elements of A and the matrix B. So might take a little while to wrap your head around it, but basically it's kind of like an element-wise multiplication in a matrix world here. So we're taking these data symbols and doing this Kronecker tensor operation with P code. So we're going to get these guys, each one of the data symbols replicated according to this, right? So it's going to be multiplied by 1 or minus 1, and you're going to get 11 of these for every data symbol coming out. So that's spreading this waveform, right? So then we create an interfering signal, and they do some stuff to try to adjust the powers and that type of thing. We've got we had some noise. I've started to add in some additional things because part of your assignment is going to be not just to replicate what they did in the exercise in a book, just be kind of a show and tell type of thing, right? But to actually also include code that compares it against the non-spread spectrum version. So just basically QPSK jammed with this cosine signal here. So here we generate the jammer, and so there's an adjustment to the frequency of this 0.12, and then we're just generating a complex exponential here. So, and then adjusting the powers for that, taking the power and converting it to an amplitude type of thing. Then we look at the spectrum of this. And so they use the p-welch command, which is kind of a fancy way of doing a bunch of FFTs and all. So that's described here. And you don't have to know too much about it, but just know that p-welch, it's doing some fast Fourier transforms kind of down deep inside the algorithm, but then it does kind of a series. If you have a huge long type of time series, it'll do a bunch of them and kind of build up a spectrum from all of that. So beyond the scope, it's more of a signal processing type of thing. Then we plot it, and we plot it on a semi-log, but it's kind of really a log, or actually not there. That's down here. So we plot the spectrums, then we calculate the bit error rates, and so we do that incrementing from from 1 to 9 dB or 10 dB here. I think it stops at 9 dB actually. So we're yeah, because they subtract 1 here actually. So we go from 0 to 0 to 9 dB, and we add some noise, and they do it kind of manually here. A lot of you all have done this approach in your previous assignments. But note in the previous assignments, we've typically calculated like a bit error rate at a particular signal noise ratio or EBNO. In this case, we're kind of iterating through, looping through a bunch of these things so we can see how the performance changes with an increasing signal to noise ratio. So they add noise and they add a jammer to the input signal, and that creates a Y out. And then there's some despreading here, which can be done just by multiplying by this P code that we have up here. And then there's some decisions that go on. Actually, it's just this one up here. So this decision then will take these things and look at the sign. Since it's just QPSK, we just need to see, is it above or below the real axis? Is it to the right or to the left of the imaginary axis to map these symbols appropriately, right? So these things are then mapped using the sign function by isolating both the imaginary and the real part, and then do the sign, and then build up the complex value again, so that these guys over here, this deck 1, now we should be back to kind of 1 plus 1i, 1 minus 1i, minus 1 minus 1i, that type of thing, or j's or whatever. So and then we calculate the bit error rate. And here, since we're in this loop, we're going to kind of append to an existing value each time. And we're going to do this comparison. So we look at where they're not equal, and we sum those up, and then ultimately divide by 2 times the L data here. So where L data is number of data points, and the 2 is kind of handling this real imaginary type part. Then for the basic case, they're using this EECE function to which is related to the Gaussian function to actually kind of print out the theoretical performance you should get. And then I've added the situations of a non-spread basic QPSK performance, and a also the jammed version, and then we plot that. So if I run that, then we will get kind of the 2-sided spectrum, both positive and negative frequencies of the CDMA spectrum, and then we get the jammed version. Okay, so we have this jammed signal here, and we see it's quite a bit higher in amplitude than the CDMA waveform here, right? And since we use a complex exponential, it's just showing up in the positive frequencies. So when we actually run that, you will see this here. And so this is for 10 dB, I think. And this is like the ideal performance with no jamming. And here it is with narrowband jamming, and this is some stuff. I'm not sure if this is right yet or not, but that would be the QPSK non-spread version of things, right? So, and then you can come up here in the book, their figure, even though their code doesn't really do it, but their figures do, I think it's 5 dB, 8 dB, 10 and 20. So here's a 20 dB uh, 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 signal to interference ratio, right? So now the signal is much, much stronger than the interference signal. And so, of course, it's going to approach the non-jammed version. Conversely, if we go to 5 dB, then we will see our performance is now pretty bad, right? So not a miracle cure, but works in general. All right, so we're going to do an assignment that's based upon that, and I'll post that on Moodle soon, and you'll be able to get started on that. All right, so now let's dive into the lecture. We're going to talk about diversity, and then multiple input and multiple output systems, and actually some of the we'll build up to that. So we know that we have these problems in our environment, and it boils down to the channel. We get noise from the channel, we get distortions, we get interferences, and all those things make it hard for us to detect or make an accurate decision on what the transmitter sent us, right? So we've talked about some ways of coping with that or overcoming those things, and they're all most of them are one form or another of diversity. And so I'll explain this via some examples, right? So with the forward error correction, so where we might use some linear block coding or convolutional code, we leverage diversity in the time domain by transmitting at least partially redundant information at different times. All right. And one of the things that I've mentioned a little bit, although we didn't really do it in our exercises or anything, but after you code it, sometimes you scramble the order in which you're sending the data. And you do that in a deterministic but pseudo-random way. And so that you can kind of do the inverse descrambling process at the receiver. And what that does is that kind of takes a block of time and moves these redundant bits. Instead of being right next to each other, they'll spread them out within that time block that we're scrambling over. And that helps us if we have kind of a bursty type of interference or noise type of event that might occur in part of that time block, but that because we have this time diversity, we can use that redundancy and try to overcome those results, right? And recover the information. We just talked about spread spectrum, where we leverage diversity in a spectrum by transmitting over wider frequency ranges than needed, right? And we see how that can help us to avoid narrowband jammers and interference. We're now going to talk about spatial diversity. In complex multipath environments, we can leverage different paths between the transmitter and the receiver, right? So we in our simple channel model, we had a transmit antenna and a receive antenna, and we just assumed there was a way that went from kind of start to finish there, and that was it, right? But then we've realized that no, there's scatters in the environment. It might bounce off the ground or the floor or the ceiling or the walls or the mountain or the building. And we have these multiple paths that go from the transmitter to the receiver, right? So we have a diverse set of these paths. Maybe that can help us overcome some of these bad or temporarily bad channel conditions. Or maybe we can just increase the capacity by spreading the symbols over mostly independent channels, right? So if we can consider that the transmission path that reflects off of one set of scatters versus another set of scatters are somewhat independent, then perhaps we can increase the capacity, right? Well, we need to actually increase the number of antennas in order to be able to do that, right? So if we just had one antenna on the transmit side and one antenna on the receive side, then all those signals are summed as currents inside that antenna, right? As all those waves travel, then they impinge upon that wire or metal part of that antenna, induce some current into there that gets transformed into voltage on the input resistance of the amplifiers, the characteristic impedance of the antenna, and then so then we have a signal, right? But everything's all summed together there by superposition, right? So let's now start thinking about if we use multiple antennas separated in space, then we can kind of intersect those waves at different positions. And if they're diverse enough, then we can get some benefits out of that, right? So first, some definitions. We're going to talk about single input, multiple output, or SIMO. We also have MISO, multiple input, single output. We have multiple input, multiple output. That basically is meaning we have multiple antennas at the transmitter and multiple antennas at the receiver. And we can implement this in a single user system, and where there's just one user at a time using this antenna system, or we can adapt this same kind of physical architecture for multiple users, okay, at a simultaneously, all at the same time. And so there's some things that we're dealing with here. There might be some closed loop channel state information. We'll abbreviate that as CSI. And I'll talk more about that in a little bit. Closed loop is when we're measuring at the receiver and feeding it back to the transmitter, or we just might use open loop channel state information. In multiple user MIMO situation, we can have what we call a broadcast channel and a multiple access channel. And these are separated mostly as downlink or uplink. And that's in the context of a cellular communication system or something that fits that model, and which Wi-Fi does also. So the idea, we have a base station and then multiple user equipment, UEs, or subscriber units, sometimes called SUs, right? And so we'd have multiple ones of those. So downlink is when the base station is transmitting and sending data to all the user equipment. And then uplink is kind of the opposite process, when the user radios are transmitting and sending to the base station, right? So uplinking that information, and we'll get to that next week in more detail. So now we have all these different antennas. We want to separate these signal flows. So in general, each receive antenna receives signals from all of the transmitter antennas, right? So if we have 4 transmit antennas and then 4 receive antennas, well, each one of those 4 receive antennas is going to pick up the signals sent from each one of the transmitter antennas. So we're going to be kind of considering how can we separate them, right? The channel can be modeled as a matrix of complex channel coefficients that represent each combination of the transmit and receive antennas. So if you've got 4 transmit antennas and let's say 2 receive antennas, you're going to have a matrix that's a 4x2 type of matrix, or maybe a 2x4, depending upon how you're formulating the problem, right? And each one of those elements in that matrix is describing essentially the transfer function from that particular antenna to transmit antenna to the particular receive antenna that is represented by that position in that matrix, right? That we'll call it M by N type matrix. So that's basically the complex gain of the channel that we measure, right? Now, if we can invert the matrix effectively, right? So you've worked with matrices, and you know there's a little process to invert a matrix, but you've got to be careful that the matrix is well conditioned, because if it's not, you can end up with singularities and problems, right? So so this is a big if, right? If we can invert the matrix effectively, then we can use that to recover the individual streams at the receiver, or pre-code it at the transmitter. If we take these complex channel coefficients and then send them back in the form of the CSI to the transmitter, then maybe we can pre-code it, right? So, all right, so I'm just seeding you information. We'll explain that here a little bit. So here's a SIMO situation. We've got a transmitter here with a single antenna and a single receiver with multiple antennas, right? So that means that we'll have multiple paths or multiple channel gain coefficients. So this would be a 1 by n type of matrix here, right? Describing the channel gain of each of these, right? So we call this receiver diversity because our receiver is the one with multiple antennas and it's probing the space. Each of these are spaced by, you know, on the order of wavelengths, right? So if you're building like a beamforming antenna array, you might space your antenna elements at a half wavelength type of thing. Here, there is a beamforming aspect of MIMO, but in general, we don't necessarily squeeze them that close together. Sometimes it's driven by the size of our platform. If it's a cell phone type of thing, we want to have multiple antennas inside that inside this case. We're driven by that physical size constraints, right? But we're spacing these antennas in order to try to get a diverse path characteristics, right? So that these channel coefficients are substantially different from each other, right? And that's how we can pick up this diversity, right? So now, how might we do this block here, right? So we've got these multiple antennas, and they each might have a filter, an LNA to it, a down converter, and ADC type of thing. And then, but at some point, we've kind of measured the signals on each of these antenna ports, and we want to figure out what is the best way of combining them. And you know, we only have one lecture on MIMO, and it's a huge topic, and so just going to give you kind of some type concepts here. So one way we can do this is simply look at this moment in time which antenna is giving us the strongest signal, right? So based upon that, where that antenna is in space, the multipath waves might be canceling out for that particular antenna at this particular time, and causing a deep fade. Well, that's not going to be a good one to use, right? The other, one or more other antennas might give you a stronger signal because they're a little bit, spaced differently. So the phases of those different waves as they travel to the receiver are different relative to each other, and they might add together, right? Or at least not cancel. So we can simply examine these and we might look at some reference signals or pilot tones that we encode into the waveform at very specific times. And we look at that and we say, oh, this antenna is giving me the strongest one. So I'm going to switch to looking at this one. And then, especially if we're in a mobile situation, or even just if our scatterers are mobile, moving, then it might switch to a few moments later that this antenna is giving us the better results. So we might switch to that one at a later time. So, we can more optimally combine the signals, as in a process called maximum ratio combining. We will go into some other algorithms, but in more depth. But basically, you can think of it as how can we take the information that's provided in both of these and combine it in such a way that we're kind of maximizing the information coming across, right? So in this first case, we're just picking the strongest one, where we're throwing away all the weaker ones, right? But those weaker ones might just be a little bit weaker, right? And so they might actually add a lot of information, right? So that's the idea there. All right, so then we can flip it around, and we can have this MISO approach. And actually kind of move this to, did I move that to a different slide? Maybe I left it on this one. So here we have a transmitter diversity type situation, where now we're going to, again, over here at the receiver, measure these channel gains. Let's send that information back to the transmitter. And now this transmitter is going to use that information to kind of create some pre-coding for it, right? Actually, there are some techniques that don't actually require that information, and that's this Alamuti type of approach. So let me actually go back here. So we can look at here at the receiver, we might have a Y, and then we have our input signal over here is X, and it is then modified by this channel coefficient H1 or H2, right? So I'm just assuming there's two antennas here. And then we pre-coded these signals with this WI or W1 or W2, right? And so if we know these, then we can choose these WIs over here so that the signals add maximally, in other words, in phase here at the receiver, right? So that would require kind of that feeding back information. There's another approach that we can use. It's very famous, is this Alamuti space-time coding example. So we'll send a pair of, and we're going to simplify this analysis by assuming that the symbols here coming in are real, right? So there might be a BPSK type of thing. And so we'll send these symbols. So we'll send a pair of them over a pair of time slots, right? And the way we're going to do that is we're going to send each symbol twice. And so we'll first send S1 on H1, right? So this transmitter is antenna, and it'll exhibit or experience this H1 channel gain, right? And then we'll simultaneously send S2 on the second antenna, right? And then in the next symbol slot, we'll flip it around and we'll send S2 on H1, but negate it, right? So we'll negate this symbol, but then we'll send S1 just as is on H2. And then over here, we'll we'll combine it. And boy, I cram a lot of math into just a few lines here. So, just trying to give you an appreciation for what's going on here. So, when we've received these signals in the first time slot, we're going to have S1 times that channel gain and S2 times that channel gain plus some noise, right? And then we're going to combine it with H1 complex conjugate, right? So we're going to we have that measurement of what H1 is, and we'll take the complex conjugate and multiply it. Well, this H1 complex conjugate times H1 is really this H1 magnitude squared, right? Times S1. And then we have H1 star, H2 star, S2, and there's some noise, right? And then similarly over here, we're going to multiply this by H2 star on the second time period. Now we have this minus S2 times H1 channel gain and S1 times the H2 channel gain plus some noise. And then that results in this, right? So now we've got two equations here and two unknowns, right? So what we're trying to do is estimate S1 and S2, right? So let's add these two equations together but take the complex conjugate of this second equation here. So here we would take the complex conjugate of this. Well, that would be H2, H1 complex conjugate, right? And that's where I'm assuming that the symbols are real, so we don't have to account for that. So complex conjugate of a real symbol is just itself, right? And so then this is also real since it's a magnitude squared. So then we sum. So we sum that. Then what we end up with is this Z1 times, or Z1 is equal to this H1 magnitude squared, H2 magnitude squared times S1 plus noise. And so then we can simply divide. So this is the S1 now that we're measuring once we're multiplying by these complex conjugates of the H1 and H2, right? So we take this Z1 and we divide that, and that should equal S1 plus some noise, right? So then we'll do a similar result for S2, right? So you get a kind of a parallel type relationship there. So should note that the noise is affected during this process, but I've just, either not carried it along, or I haven't noted that this N does get colored as it's going through the process, right? So it's no longer white. So this Al-Moody process is a very classic, famous type of pre-coding where we don't really need the channel state information at the transmitter. Okay, but let's talk about channel state information. So here what we're doing is we're typically transmitting some well-defined pilot signals, right? So at a certain time in this waveform, we will, that's generally defined by a standard, we will transmit signals at a particular amplitude and phase, right? And then, so it's not a function of the data that's coming in. Then the receiver measures those pilot signals, and since it knows what it's supposed to be, it can calculate the H matrix, right? The channel matrix, or the channel transfer function from each transmit antenna to each RX antenna. Okay, and then that forms this channel state information, and the receiver sends that back to the transmitter, and the transmitter then uses that CSI to pre-code the waveforms, right? And so there's some caveats here. is that it requires the channel to be somewhat time invariant over the time scale between these measurements, right? So it takes time to send these pilot signals, to measure them, to send it back, and maybe the next data frame, or in a frequency duplex type situation, which we haven't talked about yet. But so it takes some time, and then it also consumes capacity as overhead, because kind of in the simplistic case here, these pilot signals aren't carrying any data information, right? So they're these kind of predefined static type of signals. So they're not carrying information, so they're consuming capacity as overhead. So if we just measure it at the receiver and apply all our algorithms there, then all our combining and that type of thing, then we don't need to send it back to the transmitter, right? And that would be kind of open loop CSI type thing. But if we're sending it back to the transmitter, that would be a closed loop type of thing, and consumes even more capacity then. So, all right, now let's kind of expand. We looked at one situation where we had multiple receive antennas, and we talked about combining, and then we said, well, we can have multiple transmit antennas and kind of pre-code it. So let's generalize that, and we'll have M transmit antennas and N receive antennas. We'll look at kind of the minimum of these, and that's going to be the kind of the rank of this matrix, and that's important when we start doing things like converting matrices and that type of thing, right? So if we look at now this, how might we do all this? Let's just assume we'll focus on combining over here. And let's look at a zero forcing algorithm. Here we have this Y signal here, and that's composed of the X data times these channel coefficients plus some noise. Right now, I'm going to switch to W for noise here. So how might we extract out X? Right. So that's what we want to do, is we want to come up with the best estimate for X. Then we can take H. If we know H, we can invert it, right? Then multiply it here, and then this H inverse times H is just 1. So we'll have X plus H inverse times the noise, right? And that would give us an estimate of X. And that would work well in a low noise environment, right? So here's an issue though, right? So this H could be it's multiplying the noise. Well, if we think about it, right? So there's these, we call them channel gain coefficients, but they're usually lossy, right? We lose energy as we propagate from the transmitter to the receiver. So these are small values. When we invert them, now they become big values, right? So they're going to be amplifying the noise. So that can be a problem, right? So so we can say that it works well in a low noise environment, or a high SNR environment, right, where the noise is in the denominator. So if it's higher noise, then boy, this becomes a problem over here, right? There's another issue though, and that is if AH is ill conditioned, right? So it's low rank. It's not really maybe another way of saying that is if you remember back to your matrix inversion theory, you looked at how many of these things are linearly independent type of thing, right? So doing a lot of hand waving here, right? But hopefully you kind of remember a little bit of that. Then it's going to be ill conditioned, right? So that's kind of a way of saying that these are too similar, right? When we take the inverse of that, then we're going to have elements of these things that are going to exhibit some singularities. They might approach infinity and then really amplify the noise. So that can kind of accentuate the problem. So that's starting to give us a little bit of hint that, oh, this system actually, for it to work, really needs some diverse paths here. So normally we think of a multipath, all this multipath interference, boy, that causes these deep fades when we have these cancellations from one path, that adds out of phase to another path, and it cancels. That's a problem, right? Well, actually, it turns out that that's what we want in this case. We don't necessarily want it to cancel, but we want a diverse set of paths. If this is all free space and we don't have multiple paths going on, then we're going to end up with this kind of low rank matrix situation where this is ill conditioned. These different matrix elements are too similar to each other, and when we try to invert it, we're going to end up with these singularities, right? So, all right, here's another approach, and these are kind of taking the Hermitian of it. Again, that's a kind of complex conjugate of a matrix. We mentioned that early on in the class, so I'm just tossing that out there. Let's not talk about that too much. But now. But this is an approach to kind of improve on zero forcing, this minimum mean squared error type of approach. So we can do better, but let's consider an alternative, and that's where we can use pilot symbols, as we talked about on the previous slide, to sound out the channel and then feed back that info to the transmitter so we can pre-code it. Now, let's still want to estimate what X is. Let's take the X's data coming in here in this precoder and multiply it by H inverse. Okay, again, we're assuming we can take that inverse of the H matrix, but let's multiply it by this H inverse here, right? So now as we're transmitting, what we're really transmitting is this H inverse times X. Then it goes across the channel, and of course that then is effectively multiplying these by H, right? So this part is what we transmit, and then the channel essentially multiplies its transfer function on top of it, right? So that's what we end up with. The noise just enters the system as normal, right? All right, so now H times H inverse is just 1, right? So look at what we end up with. We end up with this X estimate, X hat, is equal to X plus W. Note that there's no noise amplification, right? This is just W. It's not this H inverse of W. It's just W. So if we want to, suffer that overhead of sending this channel state information back, and assuming that the channel is relatively stable over the time periods that we're doing that process, then yeah, we can actually do better than doing this zero forcing algorithm at the receiver. Let's pre-code it. Now, there's an even more sophisticated way of doing that, and that's a singular value decomposition approach. SVD is a very common type of mathematical analysis tool when we're dealing with data, and in particular, it's used to do like a pseudo inverse when you have a non-square matrix, right? And normally when we take a matrix, we're assuming it's a matrix, but sometimes we actually have more data than we have variables, right? So it's we might make a whole bunch of measurements, but are only trying to solve for 2 variables or something, right? But maybe we'll take 10 measurements, so we actually have 5 times as many equations as we need, right? So we put all that in, and that gives us a non-square or rectangular matrix. Now, when we try to invert that, we end up with needing to do a pseudo inverse. So SVDs used to do that. And if you've ever done a least squares fit type of approximation to data, then you've done something like this, right? This is SVD's technique that might be used. There's a number of different ways of doing this, but this is a very common way. So the point is a very common mathematical analysis tool. And what we're doing is we're taking this H matrix, which now again is this transfer function, and that we're measuring that here at the receiver. And we're going to decompose this matrix into kind of a cascade or multiplication of 3 different matrices. Now this U and V star are unitary matrices, so they kind of look like a unit matrix, but a little bit more complex than that. And then this D matrix is a diagonal matrix, right? So we just split this up using a mathematical approach algorithm to have these things here, right? So sometimes you can view these as like these U and V's are rotating the data and D is scaling the data. Yeah, so now what we're going to do is we're going to do a little pre-coding and combining, and we're going to take, let's see if we can pick this out by looking at it. So on the combining side, we're going to end up with this Y, but we're going to multiply it by the U star to get our X hat estimates, right? And you're going to see why, because we're going to take our X and we're going to start by multiplying it by V out here, okay, in the pre-coding thing. Then our channel is going to now do its thing on our transmitted signal, which is now Vx, right? And so our channel is this H UDV star, right? So that does its thing on this Vx. And then we're also now doing this U star at the receiver. So when we look at this, these have these kind of special properties. So when we multiply the V complex conjugate times the V, we're going to get 1. We're going to use a unity matrix. And the same thing over here is U star times U is going to give us a 1. Okay. And okay, we're doing this at the receiver, so we're going to multiply the noise by this U star. So what do we end up with? Okay, so those guys cancel, so we just end up with D times X, right? So we can now estimate this X hat from this D times X, and this is a diagonal type matrix, so it's easy to kind of pick off each individual value of X over here, right? And then this U star also, because it has this kind of unitary matrix type property, it's not really amplifying W. It's you just in a hand wavy way, again, think of it as multiplying by 1. So we're not getting this noise amplification out here. So it looks a little bit more complex. You just need to do this calculation, measure H, do this algorithm where we do this decomposition into these 3 different matrices and send that data back here so we can pre-code with V and then multiply by U star over here. All right, so this is single user MIMO, where we're transmitting and receiving with one link, right? So one transmitter here, one receiver here. Now, of course, we'd like our systems to be able to support multiple users, right? Whether it's a cellular system or a Wi-Fi system or something like that, right? We want to be able to support multiple users at the same time. That would be great, right? So here, as I mentioned towards the beginning of this lecture, we have this multiple access channel, and we also have the broadcast channel. So let's look at the multiple access channel first. And here's where we have multiple users accessing the channel to talk to the base station at the same time. Okay, so user one's transmitting on this frequency at this time, and all the way up to user K is using the same channel at same frequency channel, same time. Normally, we would think that's going to interfere, right? So maybe we use some spread spectrum techniques to try to isolate those, but there's going to be some interference there, right? But because we have this diversity in the paths, then we can actually separate out these guys, right? Now, here we have this joint demodulation decoding. We've got a bunch of acronyms here. Again, we're not going to go into the depths of these, but I've mentioned this minimum mean squared error algorithm before. We also have these two are kind of related, this successive interference canceller and multi-user detection, MUD. And so MUD is a technique that's commonly used in CDMA type of techniques. But the idea is basically you try to do your best effort at demodulating maybe the strongest signal coming from this user, and then you do that and you make an estimate of that user's data. Then you kind of subtract or divide out the effects of this user's information from this total Y that you received over here, and then try to decode the next strongest signal, right? So lot going on there, but we're dealing with kind of a successive a process or a repetitive kind of iterative type of process here, right? So we end up with being able to support multiple users over multiple channels at the same time, right? So multiple paths, right? So a diversity of paths. Again, clarify that this is same frequency, same time, and so normally they're interfering, but because we have this kind of MIMO type of approach, there are algorithms that allow us to extract out the data from all these guys. What's key here is that these multiple transmit antennas are really kind of isolated. So in this case, we've got user one with one antenna and user K with another antenna, right? So we're not able to like pre-code these guys here in the same way as we did in a single user case. User one just has his data, and that's or her data or whatever. That's all they can send, right? So they're just going to send their data. User K, user two, user three, they're all going to just send their data. Now, it's important that we have some timing control on all this, so that and what we call group selection, because all this data needs to be sent at the exact same time, so that when it or I shouldn't say exact same time, it needs to be sent so that the symbols arrive here at the receiver, at this base station receiver, at the same time, right? And if user one, let's say, is a little bit farther away than user K, it probably needs to start its transmission a little bit earlier than user K, right? Because it's got to travel farther. So we compensate for that distance with this timing control. If we've got a big base station, we might have a group of users that are all pretty close to the station, and we might allocate them into a group and say, okay, you guys, are in this group and you transmit at this time. And then we might have users that are farther away. And so we assign them to a different group, and maybe they transmit next, right? So they wouldn't necessarily transmit at the same time, but those that are within the same group would, right? And then they would have the fine timing control inside there, right? So all this is done to make sure that the signals arrive here at the same time, right? And so all these algorithms work. So real high level type stuff. But then we have the broadcast channel situation. And here, this is when the transmitter, or I'm sorry, the base station would be transmitting out data to all the different user equipment subscriber units, right? And now that's what we call the downlink process, right? So we're transmitting from the base station to the subscriber units. Now we can do some pre-coding and then kind of summing this all these things up to send them on these different antennas, right? And so again, user K, his or her data would be sent on all these antennas in the same way as user one on all these same antennas. So there's a process going on here. And then user one receives information from all these different transmit antennas and can take care of extracting out their data and so on down to user K. All right, so there's some acronyms here. There's dirty paper coding. That's basically a process that pre-codes data so that you can kind of cancel out interference. The original author, I think it was back in the 70s or something, that wrote this, and it's kind of basically like if you had a piece of paper that was all smudged up and dirty and that type of thing, you could still encode data, you write data on it by kind of erasing it first and then writing some data on it, or doing it in such a way that you're kind of canceling out the effects of that dirty paper. So that approach is complex, but it's pretty optimal, I guess. I'm not sure if it's truly optimal, but there are some more simpler, lower complexity approaches to it. It requires a lot of information. Here, note that the timing control and group selection is trivial, right? Because these guys here are going to do the demodulation on their own time frame, and it doesn't matter if this guy's data takes a little bit longer, the signal takes a little bit longer to get there because he or she's farther away, whatever, right? All this is under timing control, so they're all just transmitted simultaneously. So, all right, so that's so last year I rolled this over into 2 different days of lectures. So we'll continue looking here, and again, not going to worry too much about these specific equations. Just let's look at things here, right? So what about the capacity of these things, right? So are we getting the capacity boost? Well, yes we are. So there's a lot of cost involved in doing this, right? So we need a lot more hardware. We need to mount extra antennas on top of the base station tower, let's say, and you actually pay rent to the tower company, the company that owns the tower. And the more mass you put up there, it's actually driven by wind loading, the more you have to pay rent each month. You not only have to buy the antenna, but then you have to buy the space for that extra antennas up there. You need more fiber or coax cables to connect up your radios to those antennas, and you need a separate power amplifier and maybe some filters and some other RF equipment. Basically, that whole RF chain needs to be duplicated for each of these antenna chains. The same on the receiver, right? And those are typically lower cost type elements. LNA is usually cheaper in the power amplifier, but still it's a cost impact and more power consumption and that type of thing. So hopefully we do get a capacity boost, and yes we do, right? So here, this is a way of showing our power to signal power to noise power type of relationship, right? So here the capacity has been normalized per hertz, so you can assume that the bandwidth out here is equal to 1. So it's kind of a common way of looking at what we call a spectral efficiency, or bits per second per hertz. So here our power has been scaled by these H constants. So if we have multiple ones of these, then we're kind of scaling that up. Here we're scaling according to the norm, right? So here, this is just the absolute value of this H thing, but here it's the norm. So this is potentially better. So if like this HN is equal to 1, then if we have N antennas, then this H norm squared is equal to N. So here we'll get that boost by the number of antennas. So something similar is happening. Well, this is still MISO here. Yeah, so I'm sorry, this is the CISO case, single input, single output. So this is kind of the default situation. So here our signal multiplied by that single H there. And so that's, H again is normally less than 1. You might have some power amplifiers and LNAs, but it ends up getting multiplied by that channel coefficient, and so that scales your power down. Here we're seeing this for the single input, multiple output, where we're combining these things at the receiver. We're getting this boost event. So we've got a cost associated with the extra receive antennas, but we get a benefit from it, right? So in terms of capacity. And similarly, for the MISO case, same type of thing happens. Of course, this is when we're doing the pre-coding, and again, that avoids amplification of the noise with the channel gain at the receiver. And but we end up with this capacity improvement there by this factor of N. Now with MIMO, the system uses a combination of both pre-coding at the transmitter and linear combining at the receiver. And so we can decompose the MIMO channel into some number equal to or greater than 1 parallel non-interfering scalar Gaussian subchannels, right? So basically looking at all these paths from input to output and decomposing all of those, right? Now we take R as the rank of H, right? So again, this H matrix, it's got all these different, added to white Gaussian noise subchannels. And so R is this rank is going to be the minimum of M by N. M is the number of transmitter antennas, and it's the number of receive antennas. And you take the minimum of that for H to be full rank, right? And all right, so then how much time do I have? Okay, the pre-coding matrix is derived from an icon decomposition of H, the Hermitian or complex matrix version of the complex coefficient, complex conjugate, sorry, times H, and the linear combining matrix is likewise derived from that same type of math there. So, all right, so let's look this last slide and then I'll let you go. So multi-antenna needs multipath, right? I mentioned that earlier in the lecture. So let's kind of revisit that, right? So the receiver estimates the channel from known sounding signals, or these pilot signals, sometimes called reference signals, pilot tones, and they're sent by the transmitter, right? So these are known, and the receiver measures those and does that periodically so it can keep it updated. Each time it does that, it sends this information to the transmitters, this channel state information. Now, assuming you're doing pre-coding, right? So if the rays, all those different rays in terms of the paths from the transmitter antenna to the receive antenna, if they're too similar to each other, the inversion becomes numerically difficult. And when you're doing that, now you're dealing with numerical precision issues and that type of thing in your mathematics. And if you have some measurement inaccuracies here, then they can get amplified in this approach and that type of thing. So the kind of noise in that overall process can wash out the differences between each of these rays. And now we're no longer, again, kind of in a handy wavy way of saying that they're not linear independent from each other, that they're too dependent or too similar to each other. So ultimately, it is difficult to separate out the R different streams if the propagation environment is too clean. So kind of from a mathematical standpoint, we see that in order to be able to do these math functions where we're doing this inversion or decomposition or something like that, if all these paths are too similar, if we have too clean of an environment, then we're not really getting the diversity that we're trying to tap into with this approach. Okay, so be on the lookout for the assignment as I post that. I'll try to get that up this afternoon. And then next week, we will look into 5G and look at cellular technology in general. All right, have a great weekend.